Hello guys, this is third lecture in the series of digital electronics. In the last lecture we have seen different number systems, their radix and symbols. In this lecture we will study binary number system in detail. Binary number system is developed for digital circuits which use only two voltage levels for the operation, and the two voltage levels are indicated by 0 and 1 in binary number system. Thus, there are only two symbols or digits used in binary number system, and hence its radix is 2. This is binary counting shown in the table. You can see these are the decimal numbers and these are the binary equivalents. That means 0 in decimal is 0 in binary, 1 in decimal is 1 in binary, 2 in decimal is 1 0 in binary, 3 in decimal is 1 1 in binary. So, in this way each decimal number is represented with the combination of ones and zeros only. You will wonder how a big decimal number can be represented by only ones and zero, only two digits. This is possible because of the method of weightages. Here the binary numbers having their weightages, these weightages are shown here. See, in a given binary number, the weightage of bit at unit place is 2 raised to 0. Weightage of bit at first place is into 2 raised to 1. Weightage at the second place is into 2 raised to 2. So, these are the weightages, or if you calculate it, it is 8 or 4 or 2 or 1. These are the weightages of the bits at the places in the binary number. Now let us consider how a number is developed, binary number is developed. Now 0 in decimal number, if you consider the weightages, you want 0 only, so there will be no bit, and hence binary decimal 0 is 0 in binary also. If you consider 1, you need 1. 2 raised to 0 is 1. So, what is done is 1 is placed at the first place. So, here 1 is placed. For 0, there is 0. So, 0 into any place you can say is 0. For 1, 1 is placed at the unit place. So, that will give you 1 only. For 2, you need 2. So, 2 is, see here, there is 2 at the first place. So, 1 is placed at the first place. You know, you don't need 1. So, there is 0. That gives you 2 raised to 1. That means 2 plus, here there is 0. So, 0 into 2 raised to 0 is 0. So, 2 plus 0 gives you 2. And hence 2 in decimal is 1 0 in binary. If you consider 3, you can have 2 plus 1 equal to 3, and hence 1 is placed at both the places. So, here you will have 2 plus 1 is equal to 2 plus 1 is equal to 3. So, 3 in decimal is 1 1 in binary. If you consider 4, so 4 is there in the this list of weightages, 4 is already there. So, 1 is placed at the respective place and zeros are placed at the other places. So, here you will get 2 raised to 2, that means 4. 4 plus 0 is equal to 4. In this way, each decimal number is converted into its binary and the counting continues. You don't have to continue this type of method to find the big decimal number in terms of its binary equivalent. You can have directly the method to convert a decimal number into its binary equivalent. The method is called as division method or double method. Let us see what is this method. So for decimal to binary conversion, we use division method or double method. In double method, from a given decimal number, the integer part and fraction part are converted to binary separately. That means if you take an example of this number 38.65, to convert this decimal number into its binary equivalent, the integer part is converted separately and fraction part is converted separately using two separate methods. Let us consider the integer part first. For integers, what is done? The number given, decimal number, is divided by 2. The quotient is written and the remainder is written on one side. Here 38 is even number, so remainder will be 0. The quotient is again divided by 2, and again the quotient and the remainders are written. So this process is repeated till the last quotient is equal to either 0 or 1. Now there is a series of these reminders. If last remainder is 1, then it is transferred to the queue of these reminders. So it also goes as a reminder. These reminders taken in reverse order gives you the binary equivalent of given decimal number. So if you consider these reminders 1 0 0 1 1 0, this arrow indicates the direction. You have to take the reminders in reverse order. So 1 0 0 1 1 0 is binary equivalent of decimal number 38. How it is written? 38 in decimal is equal to 100110 in binary. You are dividing the number by 2, and hence every time the remainder will be always less than 2. Less than 2 means either 0 or 1, and hence all the reminders are either 0 or 1. That means the binary digits or bits. So in this way, a decimal number is repeatedly divided by 2. All the reminders taken in reverse order gives you the binary equivalent of given number. This is double method for integers. Now let us see the fraction. For the fractions, again the fraction part is taken separately and this fraction part is multiplied by 2. From the product, integer part is written separately. Integer part, this is the product, then 0.65 is multiplied by 2. This is the product. From the product, the integer part is taken separately as a carry, and the fraction part from this product is again multiplied by 2. So only fraction part is taken here and it is multiplied by 2. This is the product. From the product, the integer part is taken aside as a carry. Fraction part is again multiplied by 2. From the product, integer part is taken separately, and you can continue this. But no need to go very up to many places. That will just increase the accuracy of your answer. Here the carries are taken in forward order to get the binary equivalent. So binary equivalent of 0.65 is 0.101, right? So it is written like this: 0.65 in decimal is equal to 0.101 in binary. And finally 38.65, the total decimal number is equal to this. We have calculated on the previous page, 100,110.101. This is the total binary equivalent of 38.60. We'll solve some more examples on these conversions in coming lectures. Let us move further. Now, binary to decimal conversion. That means the reverse process. If you are given a binary string sequence of ones and zeros and you want to convert it to its decimal equivalent, the method of weightages is used. Any binary number can be converted into its equivalent decimal number using the weights assigned to each bit position. Now, weight, we have discussed it in the last lecture. Those who haven't attended the last lecture, the concept of weight, to understand the weight, we have considered a decimal number 3643. It can be expressed as 3 into 10 raised to 3 plus 6 into 10 raised to 2 plus 4 into 10 raised to 1 plus 3 into 10 raised to 0. Here weightage of each digit is calculated using the radix of decimal number, powers of a radix of decimal number. So the 3 at unit place is having weightage equal to 3 into 10 raised to 0. 4 at first place is having weightage equal to 4 into 10 raised to 1. Next is 6 into 10 raised to 2 and 3 into 10 raised to 3. So this 3 is having weightage equal to 3000 and this 3 is having weightage equal to 3 only. This gives you the number 3643. So this is the process of calculating the weightages. Radix is used, powers of radix used to calculate the weightage. So let us move towards the table of weightages. Here a binary number system has radix equal to 2 and this is the method of weightages. Here at the unit place the weightage is into 2 raised to 0. At the first place the weightage is 2 raised to 1, next 2 raised to 2, 2 raised to 3, 2 raised to 4 and so on. And their decimal values are, this is 1, 2 raised to 0 is 1, 2, 4, 8, 16, multiple powers of 2. And here on the right hand side of decimal point, this is for the binary number. So this point is binary point. Here these are the decimal numbers. So this is decimal point. On the right hand side of the point, the weightages are like this. Here the weightage will be calculated using the bit into 2 raised to minus 1. Here it will be the bit into 2 raised to minus 2. That means it is divided by 2 raised to 1 or 2 raised to 2 or 2 to 3. The bit will be divided by the powers of radix 2, right? So by using this table you can calculate the decimal equivalent of given binary number. Here an actual example is taken. To convert 1010 in binary to its decimal equivalent, see what is done. 1010, this 0 is at unit place, so its weightage is calculated like this: 0 into 2 raised to 0, this 1 into 2 raised to 1, this 0 into 2 raised to 2, 1 into 2 raised to 3, right? Now calculate them. This 1 into 2 raised to 3 is 8. This is 0 into something, so it is 0. then this is 1 into 2 raised to 1, that means 2, and this is 0. 8 plus 2 is equal to 10. So 1010 in binary is 10 in decimal. Again, what about fractions? Take another example with fractions. This is integer part of binary number 10110.101. So by using the table which we have seen, this table, how the weightages are calculated. See here, this is the binary point, then this is a number at unit place. So 1011, actually this should be 0. Sorry. So this is actually 0, 10110, and then 0 into 2 raised to 0 plus 1 into 2 raised to 1 plus 1 into 2 raised to 2 plus 0 into 2 raised to 3 and 1 into 2 raised to 4 on the left hand side of binary point, and on the right hand side of binary point this is 1. So 1 into 2 raised to minus 1 plus 0 into 2 raised to minus 2 plus 1 into 2 raised to minus 3. These are the weightages of these bits, right? So after calculations, this gives 0, this gives 2, and this gives 4. Again there is 0 here, so this gives 0, and this is 14. And on the right hand side, 1 divided by 2 raised to 1, that means 1 half, that means 0.5. So this gives 0.5, this gives 0, and this gives 1 divided by 2 raised to 3, that means 8 is equal to 0.125. So if you calculate together, it gives you 22.625, right? So 10110.101 in binary is equal to 22.625 in decimal, right? So we'll solve some more examples on this conversion also in the coming lecture. There are some phrases used in binary number system, and we should know these phrases because we are going to use these phrases in the further discussion. Bit. A binary digit 0 or 1 is referred as a bit. Comes from this BINT. Binary digit is a bit. String. A group of binary digits, it's called as string. This is an example. This is a group of ones and zeros, group of binary digits. This is called as a string. Next, LSB. LSB is least significant bit, the rightmost bit in the string of binary number. You consider string, actual string here, then in the string of binary number, the rightmost bit is called as LSB. LSB means least significant bit. Least significant means its weightage is minimum. Weightage is lowest weightage. This bit is having the lowest weightage. Okay, hence it is least significant bit, LSB. Next is MSB. MSB is most significant bit. It is at the leftmost side of the given string. So leftmost side, this is MSB. MSB, most significant bit. Most significant means it has the maximum weightage in the given string. Next is Nibble. Nibble is group of 4 bits. This group of 4 bits is called as a nibble. So in this string there are 2 nibbles. 1001 is 1 nibble and 1010 is another nibble. This is group of 4 bits. This is 1 nibble. This is group of 4 bits. This is another nibble, right? So nibble is group of 4 bits. Byte. Byte is a group of 8 bits. So here this string is having 8 bits, so this is a byte. Okay, So byte is group of 8 bits, and word, a group of 16 bits is called as a word. So if you add still more 8 bits here, then it will become a word. This is an example. There are 4 nibbles, 1 2 3 4. Group of 4 nibbles is a word, or group of 2 bytes is a word, or group of 16 bits a word. Now there is one more concept called as signed binary number. How to indicate that number is positive or negative in binary number system using 1 and 0. So what is done is, in a signed binary number, the most significant bit, the bit at the MSB position, is used to represent the sign of binary number. If 0 is there at MSB position, it represents the number is positive, and if 1 is there at MSB position, it indicates that the number is a negative number. For example, in an 8-bit signed number 0 1 0 0 0 1 0 0, the 0 at MSB position, this 0 at MSB position represents the sign, because this is signed binary number. So 0 at MSB position means the number is positive number. So it is positive with magnitude, decimal equivalent of the remaining part. That means 1 0 0 1 0 0 1 0 0 0 1 0 0. It is plus 68. 0 indicates the number is positive, and this is the equivalent of 68. So this is actually plus 68. But if there is 1 at MSB position and the remaining part is same, then the number is negative with magnitude 68. So this will indicate minus 68. So in this how signed binary numbers are also indicated using the 0 and 1 at MSB position. There are some examples, some questions given on the part that we have studied right now. Try solving these examples, and in the next lecture we are going to see octal and hexadecimal number systems in detail.